Hello Science Junkie. In today's video we're going to talk about the propellers of small planes. And have you ever stopped to look at their geometry? Why do they have those crazy curves? If you notice, the same thing occurs with ship or submarine propellers and helicopter blades. All of these have something in common, and that's that they're spinning. Our intuition suggests it's related to spinning, but we shouldn't rely on intuition. We must always prove it scientifically. That's why today we're gonna see why engineers from many years ago started giving these curves to propellers. Let's get started. 3, 2, 1, go. Alright Yankee, as always, let's start from the basics, and it's actually pretty common to see. This image refers to a plane that's cruising, and here we have 4 forces since the plane is cruising. This means it has no acceleration because all forces must cancel each other out. Among all of them, what this means is that the lift force has to be equal to the weight, and the drag force has to be equal to the thrust provided by the engines. And that's because propellers work exactly the same way as airplane wings. In small planes with the propeller, what you're going to get is a forward force, that is thrust, while with the wings, you're going to get an upward force. But achieving this force requires truly understanding propeller geometry. Let's first look at an airplane's wing. This is the equation for lift force. This term here is the force we get as a result, that is the lift force. It must be greater than the airplane's weight to avoid falling. The first letter is the air density, and we can't do anything to change it. It's out of our control. We'll include the number in the equation, but can't change it. Next, we'll see how the other terms in the equation can be changed. The second term is the wing area, which can be changed with flaps or slats. This is the lift coefficient, which I'll discuss with you shortly. The last term is speed, and since it's squared, it's the most important part of the equation. I already talked about this in the video I'm leaving for you here in the corner about how I made myself a suit to fly. The lift coefficient, what it's telling us. Do you put a wooden board? This way, you won't generate any lift force because the lift coefficient will be 0. And it cancels out the whole equation because any number multiplied by 0 is going to be 0. But nevertheless, if we start to tilt the board, the lift coefficient will start to increase, and that's when the lift force will be created. For example, during takeoff or landing, the speed is low. So since we've said that speed is the most important factor, all the other terms in the equation need to increase so that the lift force remains quite large. We've discussed increasing the area, but it's more interesting to explore how to raise the lift coefficient. The simplest way to increase the lift coefficient is to change the angle of attack of the airplane. It's exactly the same as what happened with the wooden board. When you had the wooden board placed horizontally, it didn't create any lift force. As you tilt it, it does produce lift force, so here it's exactly the same. What happens is that the airplane, when it's in a horizontal position, does produce lift force. And you might ask, why am I telling you this? If this was meant to be about propellers, understanding their geometry requires knowing what I just explained. As I mentioned in the linked video about rotations, I covered everything. The farther you are from the center, the faster you spin. What this means is that the propeller, which we've already said works just like an airplane wing, when it starts spinning doesn't have the same speed in all parts of the propeller. Comparing 2 points on a propeller, one near the center and one farther out, their speeds differ. So there has to be another term in the equation that changes, and this is the lift coefficient. And the way to change it is by giving it more angle, just like what's done with airplanes. You give it more angle to get a higher lift coefficient. Remember the table. When we placed it horizontally, it didn't create any lift force. However, as we tilted it, it did create lift force. Well, this is what they're trying to do. With the twist given to the propeller, they compensate for the low speed near the center by using a greater angle so that the same force is produced. Once this is completely clear, we see it applies to all propellers. Otherwise, you'd lose significant efficiency. And another very important thing is that generally the speed at which the propellers are rotating usually doesn't change. If you want more power, you're asking the engine for it, like when you need to take off. What will happen is that the angle of attack of the propeller will automatically change, so that when the angle of attack increases, the entire propeller does too. In the equation, the lift coefficient increases, and as the lift coefficient increases, the force you get will be greater. However, you will consume more fuel. This is exactly what happens with helicopters when you need more power. The blades don't spin faster. What happens is that they change the angle of attack of all the blades, and by maintaining the rotation speed, they achieve more force. Of course, you also have to burn more fuel. But that's not all, because look, let's take the propeller and make a cross-section of it. Of course, what you're going to see is an airfoil because, as we've said, propellers are the same as wings. Instead of moving forward, they gain speed by rotating. It's the same thing. The point is, since it's moving forward, it will see wind from this direction, but since it's spinning, it will also see wind from another direction. By adding vectors, you'll see the wind coming from this direction. As mentioned, the rotation speed stays constant. What happens is, imagine now that the plane starts moving forward faster, the propeller is going to see the wind coming at a higher speed. In other words, this arrow is going to be bigger, and since this arrow is bigger, when you add the vectors, the angle at which the propeller sees the air coming has changed. Does this mean it would be losing efficiency? So what the propeller has to do is, as you move forward faster, it has to change the angle, not lose efficiency. And I haven't told you this, but I'll say it again, propellers are the same as airplane wings. And sometimes condensation forms on airplane wings. Well, this can also happen on propellers. Look, I'll leave you a video here so you can watch it. I'm not joking, okay? What you're gonna see isn't your imagination. It's not an optical illusion or anything like that. It's not the condensation that's forming on the propellers. If you want to know why condensation happens, check out the video in the corner where I explain it. You've probably seen a lot of photos of World War II planes, and if you look closely, almost 100% of the planes in World War II ran on propeller engines. These engines were piston engines, similar to those found in cars. But today's small planes, for example commercial planes like the Aerei da Trasporto Regionale or any of those planes, don't run on pistons. They're what's called turboprops, which work quite similarly to a turbofan, which I already explained in this video here that I'm showing you. Well, here we have a turboprop from the Aviacar, this plane that you can see right now. So this works as follows. The plane is moving forward, and as it moves forward, air enters through here, through this duct. Well, what they've done is make it as if it were a cut and remove the outer part so you can look at the engine. I mean, actually, there would be a wall here covering it. The thing is that the air comes in through here. That's a compressor that compresses the air, another compressor that compresses the air. The air goes in through those little, so to speak. They're not pipes, but thin parts where air can pass through. It reaches the combustion chamber. In the combustion chamber, it explodes. And when it explodes, it reaches the turbine, which is all that you see there. That spins, and when it spins, it turns the compressor and the whole accessory gearbox. And the thing is, and here's where it gets interesting, and instead of directly spinning this, the propeller, what happens is that, what it does is that it is, when the perfect, an inu. Newton's law or conservation of angular momentum. The propeller makes you spin the opposite way, just like with helicopters. Helicopters are spinning the blades, and the blades are making the helicopter spin in the opposite direction. And that's why you absolutely have to put the tail rotor. I explain all of this in this video right here, okay? But the problem is that airplanes don't have a tail rotor. How do they solve it? Well, it would simply be compensated with the tail stabilizers. But now imagine that we have two propellers, of course, one on each wing. I want you to tell me in the comments, which direction do you think the two propellers should spin? Everyone has seen a small plane with two propellers at some point in their life, but very few people have actually asked themselves this question. So Yankee, leave your question in the comments and I'll answer it next video. I hope you enjoyed and understood this video. Honestly, the rotation of the blades is a topic that really interests me. For example, when you go faster, you must increase the propeller's angle of attack to maintain efficiency. Everyone knows that small planes are for short trips, but it's really not because of the distance you have to travel, but because if you have to take a very long trip, you'll climb higher into the atmosphere for less resistance and faster acceleration. propeller planes would become much less efficient at higher altitudes. And that's why they're simply used for short trips, where you don't need to climb very high and then come back down. Oh, by the way, I almost forgot. This is called a prop fan. I'm serious. Does this really exist? Quite a few studies were done on this around the 70s and 80s more or less. They really do spin in opposite directions, and it's unbelievable. But they're super efficient. Really efficient. The thing is, they have some downsides, and one of them is that they're super noisy. Seriously, it's not a joke. They're just too noisy, so much so that even though they're super efficient, they're not used because of this issue. Because apparently from what people say, if you're inside the plane, you'd have to shout, literally shout to the person next to you so they could hear you. Of course, nobody would get on that plane, because imagine 2 hours with an incredibly loud noise in your ears. You just can't, it's impossible. Yankee, I hope you liked the video. Click the link here to subscribe for more videos like this. I'll leave a link here so you can see amazing things about planetary orbits. You know, Yankee always prioritizes hardcore science.